Morning. This is a lesson for Chapter 5, Lesson 5.2. It's in Chapter 5, discussing congruent polygons for geometry. So let's go ahead and begin. Let's talk a little bit about notation. So let's take two triangles here, which are going to be denoted as being congruent polygons. Figures are not going to be completely congruent. They're actually just congruent or not. They're not kind of congruent. They're not somewhat congruent. They're either going to be, in order to be congruent as figures, it means that all of their angles and all of their sides correspondingly will be congruent. So our congruent statement here is the following, that we have triangle ABC congruent to triangle DEF. It's actually rather straightforward the way that this is done in mathematics, that in order, the corresponding parts like A and D are going to be associated with each other. So in other words, because A is the first letter and D is the first letter listed in these polygons, it means that these two are going to be congruent. Moreover, B is the second, E is the second, right? Therefore, those guys are going to be congruent. And last but not least, C and F, being the last of the coordinates that are listed there, the last of the vertices that are listed there, are going to be congruent. So our angles, because we have three angles in our congruent statement, are going to be A congruent to D, B congruent to E, and C congruent to F. All right, so moreover, what we start to look at now is that we have three angles. Of course, for a triangle, it's going to be three angles and three sides, right? So the next up, we have AB congruent to DE. It's the first and second, congruent to the first and second. Sorry, it's not an angle, it's just a line segment. AB congruent to DE. The next is going to be BC, which is going to be congruent to, right? It's the second and third. Has to be EF. And I have to use two tick marks because I've already used one tick mark. Okay. So, again, second and third BC, second and third EF. BC congruent to EF. And last but not least, we have AC, which is congruent to DF, the first and third, right? The only other combination that we can make. First and third, A and C, first and third, E and F, in terms of how they are listed. So it's really nice. It's pretty straightforward. Don't really need to overthink it. All the vertices are going to be in order and correspond to one another. These are the corresponding parts of those congruent triangles. Next, let's consider the following congruent statement. We're going to have ABCD, which is going to be congruent to JKLM. Kind of funny here that we have that, right? Because we're just discussing a triangle, but this indeed is actually not a square, it's actually just a quadrilateral. I think the default quadrilateral we have in mind is going to be a square. So let's kind of divorce ourselves from that. We don't know what the figure looks like. We just know that we have four vertices that are listed. Therefore, it has to have four angles and four sides. Here's actually what our quadrilateral will look like. I'm going to kind of do my best to draw this. It's a, software I'm not having corrected because I don't want to make this look like like a square, because it's just not what it is, or a rectangle. This is just a quadrilateral, A, B, C, D, and we have J, K, L, and M. So we have our corresponding parts. These guys are going to be congruent, okay? And here are some dimensions. AB is 8, DC is 12. And we have some angles. Angle A is 102 degrees. Angle D is 84 degrees. And angle C is 68 degrees. And then we have JKLM. JK is going to be x minus 2. And then M is going to be 3x plus 2y degrees. And what our problem is going to tell us to do is that we need to solve for x and y. Well, we know our corresponding parts are congruent, right? So here we have, we're trying to just solve here, and we're going to solve for x, and x is located in two places. It's located here and here, but the one where it's by itself, it's not two variables, is an angle M. Now, angle M is the last angle listed. Therefore, it's going to be congruent to D, right? It's the last thing. But again, that's 3x plus 2y. It's two variables, and I don't know how to solve that, right? Unless I have a second equation that's in two variables. So looking down here, I have jk, right? Right down here. Well, side jk, that's the first and second. Well, the first and second listed in the other quadrilaterals AB. So AB and JK are of course equal. Therefore, JK, which is x minus 2, is equal to 8. So we can solve for x, which is equal to 10. That's pretty straightforward. Now again, what we had just discussed, we have angle M, right, which is equal to or congruent to angle D. It's the last vertex listed. So M, which is 3x plus 2y, is equal to 84. Again, I can't solve that in two variables, but hey, I already know what x is equal to. It's 3 times 10 plus 2y, and that's 84. Right? 3 times 10 is 30, plus 2y is 84. Continuing my algebra, I'm going to subtract 30 from both sides as I'm working to get y by itself. I'm left with 2y on the left side is equal to 54. And to get y by itself, I divide both sides by 2, right? And now y is going to be equal to, those guys factor out, 54 divided by 2, according to the calculator, is 27. So there we go. We have a solution. All right, next, moving on. Remember, all your angles and all of your sides need to be, that we don't have any other way to demonstrate that we have congruent triangles right now, right? So I'm going to draw two triangles. I'm going to share a side here. These are A, B, C, and D. And a few little pieces of information are given in the diagram. It's this. A and C are going to be congruent. Moreover, AD is parallel to BC as well as being congruent. Also, AB is congruent to DC. So what we're going to be doing is we're going to show that triangle ABD is congruent to triangle CDB. All right, so here we go. What we're working with here is that we're going to show that these triangles are congruent, right? All the angles and all the sides, right? Just demonstrating that these are two completely congruent triangles. And again, the notion of being completely congruent is kind of silly, right? It's either just going to be congruent or not. So in this case, though, what we do need to do is make sure that we're showing, again, all three angles, all three sides are going to correspond to something in the other triangle that we have. All right. Something to keep in mind here is the need to be so explicit in anything that we argue. So one of the things about this course is that I hope that it actually helps to improve your academic writing. One of the things about academic writing is that it doesn't necessarily need to be filled with detail, and it needs detail, but it doesn't need the sort of detail that prose needs, right? Some sort of like an artistic narrative. It needs to be explicit and to the point, okay? It's rather formulaic. So we need to, here is to sufficiently make our case, we need to show every single angle corresponds to an angle in another triangle, as well as every single side corresponds. So let's first work on the angles. The first thing we're given is that we have angle A, which is congruent to angle C. And that's just right in our diagram, given in our diagram. So we need to demonstrate the other angles. Well, one of the giveaways and very popular in geometry books is that we have parallel lines which are going to create BD as a transversal, meaning that this angle right here and this angle right here are going to be congruent, right? So that angle, which is ABD, is congruent to angle BDC. And the reason why is because with those parallels and that transversal BD, we have created alternate interior angles. Again, a very popular thing in geometry books. The other one is typically whenever we see intersecting lines, we're going to have vertical angles that come out of that. So that's something we should kind of take away from the diagram. Well, the same way we had alternate interior angles on one side, we have them on the other, right, of the transversal. So again, we have angle DBC, which is congruent to ADB. And again, that's because these guys are alternate interiors. So we've now made the case and we've demonstrated every single angle is congruent. Now correspondingly to each triangle. Now we need to do that for 3 sets of sides, okay? So we have one that's, actually we have 2 of them that are just given to us, right? Just marked in the diagram. AD, let me rewrite my D there. Came out a little funky. AD is going to be congruent to BC, that's given. As well as AB is congruent to CD, which is also given. Now, we have to be explicit about the last line that's going to be congruent. And we have BD being congruent to itself, right? BD is congruent to DB. DB. Same line congruent to itself. Gentlemen, this shows the intellectual necessity for the reflexive property, something equal unto itself. And it's so important because there's no justification otherwise without that reflexive property. So there we go. We have our 3 sets of angles, 3 sets of sides. I think we kind of all snickered once upon a moon about the notion of the reflexive property. Like, it's kind of silly. Why would we need to say something's equal to itself? Of course it is. It's obvious. But as obvious as it is, we need to make sure that we're still giving reason, that we're being explicit in our argument. All right. Next. Draw a couple triangles. We have A, B, C, and we have Q, R, S, and we have angle B, which is congruent to angle R. And we know that angle B is 52 degrees, is what we're given, and all we're going to do from there is we're going to find the measure of angle S. Well, this I hope is very straightforward, and it's actually going to illustrate one of the next theorems that we're going to do, which is the third angle theorem. We know that since B is 52, then R also has to be 52, right? And then so we know, right, we had a theorem that gave us, it was a corollary that gave us the sum of these 2 angles in a right triangle, right? Which is going to be, they're going to be complementary. So 52 plus something is 90, so take away, we're going to get 38 degrees, right? And that's angle C, which also has to be angle S. Again, this is demonstrating what's known as the third angle theorem, which the third angle theorem says that if we have 2 angles in one triangle that are congruent in another triangle, then the third angle is congruent. Okay, it's rather nice. Pretty straightforward though. I'm not going to do the proof for you, but I'm going to prove it. I'm not going to actually do the 2-column proof. It's going to come up actually probably in your homework, or an exam somewhere. So I'll explain how to do it, right? Again, A plus B plus C is going to be equal to 180. Q plus R plus S is going to be equal to 180 because these are triangles, right? Sum of the interior angles of triangles, which is a theorem we have. So we know that since both equal 180, the sum of A plus B plus C is equal to Q plus R plus S, right? Because that's transitive, right? And then moreover, we have A and Q equal, right? and we have B and R congruent, right? So we could use those to substitute with each other, right? We could say that A plus B plus C, we could substitute Q and R with A and B and say that A plus B plus C is equal to A plus B plus S, right? Take away A and B from both sides, and you know that C is equal to S. All right, last but not least for today, we're going to do a little proof here. So let's go ahead and draw this diagram. Okay, we have a right angle here, we have a right angle here. The names of these are W, X, Y, V, Z, and then we have some congruent parts, right? WX is going to be congruent to VZ, XY is going to be congruent to YV, and WY is congruent to YZ. And we are going to show the following. First of all, we've been given a lot of information, okay? We've been given that angle X and angle V are right angles. Moreover, we've been given a bunch of congruent segments, right? WX congruent to VZ. We have XY that was congruent to YV. And last but not least, we're given that WY is congruent to YZ. And here's what we're going to prove. We're going to prove these triangles are congruent, okay? Now, we don't have any theorems that give us any shortcuts here where we need less proof to make our case, right? We need to show that all the angles and all the sides right now in this course so far are going to make our case for us. So here we go. Statements, reasons. So we need to be explicit about all three sets of both angles and sides. And again, we're just going to rewrite our given here. Angle X and angle V are right angles. And of course, all these congruent segments that we have, we'll just detail in right here. As our given. Okay, so X and V we haven't detailed as being congruent. So we have all the sides being congruent, right? Now we need just to demonstrate all the angles. So first of all, we have angle X congruent to angle V. And that's because all right angles are congruent, okay? They all equal 90, so therefore they're congruent. Let's keep going. We have angle WYX, which we know has to be congruent to angle VYZ. Now remember what I said earlier with the kind of the giveaways from these geometry problems and very popular in geometry books. Anytime we have intersecting lines, try to look for the following. We have some vertical angles, okay? Now, in our triangle, we have two sets of angles that are congruent. Therefore, let's use our brand new theorem. We know angle W is going to be congruent with angle Z, and that's our third angle theorem. So then I think we're home free here, right? All three sides, all three angles have been demonstrated to be congruent. There, we have proven WXY, right? We have demonstrably given proof with all of those various parts, triangles ZVY, all those various parts being corresponding parts, which we'll actually have a little name for that as we move forward. Okay, so that's all I got for you for today. Good luck, and of course you can contact me if you have any questions, and go ahead and get started in Canvas.